This material has been reproduced and communicated to you by or on behalf of the Australian National University, in accordance with Section 113P of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further reproduction or communication of this material by you must be consistent with the provisions of the Act. Do not reproduce this material. Do not remove this notice.
Okay, hi everyone. So last lecture we started looking at matrices and we got caught in the middle of doing vectors. So I'll go through that again a little bit and then we'll move on to the more important stuff with matrices, which is linear operators. Okay, so let's remind ourselves what we defined a vector as. So we have some n, which is just some positive number, whole number, and it's kind of like the dimension of our space that we're working in. So an element of this Cartesian product of the fractions will be called a vector. And you can think of these, say x, if it was two-dimensional, then you could probably image this as like just a 2D Cartesian plane, and so this would be like some n-dimensional space. And so this would be like the coordinate in one direction, and then x2 is the coordinate in another direction, perpendicular to it. So that's kind of like the motivation of why we would define vectors. And, well, maybe you've seen vectors before, and you have this idea of them as being these sort of, I guess, line segments with a direction as well. And, yeah, and the way that you'd add them is you put them like head to tail, and things like that. So all of the calculations we do will fit with that sort of idea of a vector as well. Okay, and so since we're looking at matrices, you can think of vectors in two different ways. You can think of them as a row vector. So this is just going to be a vector with one row and n columns. Or you can think of them as a column vector. So this is going to have n rows and just one column. And so the sum of two vectors, x plus y, is very easy to define. So x plus y is just equal to adding the components together. So each coordinate, x1 plus y1, goes in the first coordinate, and so on. And, well, if you're adding vectors, then you want them to have like the same dimension, and when you're thinking about matrices, that means they need to have the same shape. And as I mentioned before, there's different ways to define products on vectors, but we're not going to look at the product between two vectors in this course, so you don't need to worry too much about that. And we instead have this definition that we do need, which is if we have some just number, lambda, we're going to call it a scalar. And if we want to take the product of this scalar with a vector, then it's going to be called the scalar product. And what we do is we just multiply each coordinate by this lambda. And the way that you should think about this is maybe if you had some vector, then if you multiply it by 2, then it's going to be the vector in the same direction, but it's going to be 2 times the length. Okay, so we didn't get to this stage. We're going to look at some examples. So let P be a vector in Q3, and it's going to represent the state of an ecosystem with P1 up to P3 being sizes of different species of population of 3 different species. And if P1 increases by 10, P2 increases by 20, and P3 loses 20, and P3 increases by 2, then, of course, the new ecosystem is going to be the sum of these two vectors. And so what's this going to look like? If you sum them together, this is just P1 plus 10, P2 minus 20, and P3 plus 2. So that's our new vector. And so another example we can look at is if we have these, this vector in n-dimensional space representing the amplitudes of different harmonic frequencies, so different multiples of our fundamental frequency f, then if we multiply this vector by 3, all we're doing is we're representing the same sound, but it's 3 times stronger. And so you're just multiplying the amplitude of each different frequency by 3. Okay, so that completes how you work with addition and scalar multiplication of vectors. Vectors are a type of matrix if you write them out as a row vector or a column vector. So we're going to go to the more general case of having just a general matrix and see how we add and scalar multiply them. Okay, so if we have two matrices, A and B, and we're going to assume that they're square matrices n by n, then, and we've also got this scalar number, lambda in Q, we're going to define the sum and the scalar product in the following ways. So A plus B is going to be this matrix plus this matrix, and all we do is we add the specific positions. So the row I, column J position, we're going to add both components of those matrices together to get the sum. And then if we multiply a matrix by a scalar, then all we do is we change each entry into lambda time the original entry. So this is kind of, I don't know, a little abstract, so working with an example makes it much easier. So if you want to sum these two matrices, then of course 1 plus 5 is 6, 2 plus 6 is 8, 3 plus 7 is 10, and 4 plus 8 is 12. So you need to be careful that you can't sum matrices if they're of a different shape. They need to be exactly the same shape. And if you want to take a scalar product of lambda with a matrix, so 5 times this matrix here, then we just multiply each entry by 5. So 5 times 1, 5 times 2, 5 times 3, and 5 times 4. Nothing too tricky. Okay, so we're going to move on to something called linear functions, and this is kind of the motivation of why we're interested in matrices, because linear functions and matrices are basically interchangeable in some sense. So let's define what a linear function is. So in this course, we're going to focus on linear functions from an n-dimensional space to the same space. We're not going to do anything tricky where the dimensions are changing, or maybe the sort of field that we're working over is a little bit different. So rather than fractions, we might go from fractions to reals or something crazy like that. But in this course, we're going to focus on same dimension, and we're over the field of fractions. Okay, so a function is called linear if and only if it satisfies the following two conditions. So the first one is if you take the function and you apply it to the sum of two vectors, then it's the same as applying the function to the first vector and then adding it with the function applied to the second vector. And then the second rule is something kind of similar. It is that the function applied to the scalar product of lambda and x is equal to lambda times the function applied to x. And so this is something you see throughout mathematics. So if you've got this structure, so we're working over vector spaces, and the way vectors work is you have these rules that says the sum must work in this way, and we've got this scalar product that must work in this way. So then a good definition of what a function is on a vector space is that it respects these sort of addition and multiplication. So if you do more math subjects, then you'll see very similar things in all different fields of maths. Okay, so let's look at an example of a linear function. So for all n in the natural for some n in the natural numbers, suppose we've got this a1 up to an representing amplitudes of different harmonics of a note played on a violin. So a1 is going to be the amplitude of like the first harmonic and then so on. So an is the amplitude of the frequency nf, where f is this fundamental frequency. And we're going to define a function which maps this set of amplitudes, sequence of amplitudes, to just cutting off some. So we're going to take an m less than or equal to n, and we're just going to dispose of the sort of the higher rated frequencies. And so people call this a filter. You're filtering out the higher frequencies. And so it is a fact that this is a linear function. And the way that you prove it is first you have to agree that this is actually a function. So that's this part of the definition. And then you need to show that it's linear. So you need to take maybe this vector and something called b1 up to bn, substitute them into here and see what it equals, and then substitute them into here and see if that they're equal. And then do the same thing, fix some scalar and substitute a in as well and see that these are equal when you apply this function. So that's how you'd prove that this is a linear function. I'm sure you'll see examples in the workshops when you get to it. Okay, so we'll look at another example now. So we're going to let Pn be a subset of Q squared, and it's going to represent an ecosystem with two species at, say, time n. So we're going to start at, I guess, maybe time 0 or time 1, depending if this is going to include 0 or 1. And we're going to say xn is the population of the species 1, and yn is the population of the species 2 at time n. And so we're going to define this sort of formula, implicit sort of relation between xn's and yns. So for all n in n, xn plus 1 is going to be 4 times xn minus yn. And then yn plus 1 is going to be yn plus 2xn. So maybe you can think that, well, this number is kind of representing, well, if you've got lots of xn's, then maybe they're breeding, so then you get 4 times as many after 1 year or something. And then there being this yn, maybe it's a predator or something. So it's eating them, so that's reducing the number a little bit. And then this yn plus 1, maybe if it's a predator, you can say, well, it increases because its number's sort of preserves because it's got this previous number, and then increases more if it's got enough food to eat, basically. Okay, so remember that P is a vector, so P is equal, so this thing here is equal to xn plus 1, yn plus 1. So it's that vector. And what we want to check is, what we see here is we're going to define a function f that acts on Pn and it sends it to Pn plus 1. So all this means is it's acting on the vector Pn, which is this xy, and it's going to send it to 4x minus y and 2x plus y. So you can see that this function is modeling going from xn, yn to xn plus 1 and yn plus 1. And so you can check, again, I recommend you do check these, that the function is linear. So go back to the definition, check it satisfies all the conditions. If I was to add in a random term, just some number like 5 here, then it definitely wouldn't be linear. And maybe you can have a look at that example and see why it fails. But yeah, I definitely recommend that you practice proving things are linear. And so this example is going to recur throughout this lecture. and it continues on this slide as well. So what we want to do is we're sort of motivating why linear functions and matrices are connected in some way. So what we want to do is we want to express our function that we've created, this function f, and we want to express it using some sort of matrix. And then we're going to use that sort of expression to motivate why we define matrix multiplication in a certain way. Okay, so yeah, this is what I was meaning. We want to change this function into just some matrix which acts on the vector in some way by some multiplication or product, and so we need a suitable definition for that. Okay, and so the normal way that you write matrix multiplication between a matrix and a vector is you'll change the vector into a column vector. So in this case, it's got two components, so we write it as the vector, this should probably be a p or something, is xy. And we want a matrix M, and to define this sort of multiplication between M and x, this vector xy, that we get this answer here. And I'm going to just say that maybe this matrix here looks like a good candidate. And the reason why is when we define our matrix multiplication, this 4 is going to multiply with the x, and this minus 1 is going to multiply with the y, and then you're going to sum them together, and that's going to go into that position here. And then you go to the second row, and you'll do 2 times x plus 1 times y. Yeah, so as long as we define the product in a nice way that it's like this, then we can do this sort of transfer of a linear function into a matrix. Okay, so let's define exactly what I was saying on the previous slide. If we've got our matrix A, and it's going to be a square matrix, and we've got a vector x, we want to define the matrix vector product, and we write it as AX. We don't put like a multiplication symbol for anything. We don't put a dot or anything like that. We just write the things next to each other. Then this product is going to be defined by this matrix here. And, well, actually, this is probably, yeah, this is defining a vector because we're writing it inside Qn. And so maybe I'll expand this out a little bit. So in the first position of the vector, we're going to have A1j times xj and summed over j equals 1 to n. So this is like multiplying the row with the column vector, each component moving along. We'll see some examples after. And then the next one's going to be A2j times xj, j equals 1 and n, dot, 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 up to the sum j equals 1 and an j xj. So you see that we're just moving through the rows, and so the first row multiplied in this multiplying coordinates and then summing them together will give you the first component, then the second row will give you the second component, and then the nth row will give you the nth component. Okay, so this sort of abstract definition of what the product looks like is pretty hard to remember. I think it's easy to remember it just by sort of the geometry. If you move along this and then you multiply like that, you move along this and you multiply like that. And so this one will go here. So A11 times x1, A12 times x2, and so on, A1n times xn, and then sum them all together. If you're familiar with dot products, then it's this vector dot producted with this vector is all that this is here. Yeah. Okay, and so we've got an example here, and I'll show some of the working. So for the first term here, what we need to do is we multiply 2 with 1, so we get 2. Then we sum it with 0 times 2, so that's 0. and then we sum it with -1 times 3. So that's -3. And then the second term is 0 with 1, 0, -2, and 6. And then -1 plus 4 plus 0. And you can see that it works out exactly to this. So you'll get a bit of practice of this in the workshops, but yeah, I recommend maybe you can make up your own examples as long as you make a square matrix and the column vector as being like the same size. Does anyone have any questions about matrix multiplication with a vector? There's a good chance that lots of you have already seen this before, so. Okay, and so what we want to highlight here is, so in our example, we had this linear function, and we managed to find a matrix that imitated this function via changing the vector into a column vector and then defining matrix multiplication in a certain way. And so this is not a coincidence, and so it's not part of the course to understand the proof or anything like that, but you should know it. So if you have a linear function from Qn to Qn, then there is actually a matrix M such that this linear function applied to the vector is equal to the matrix multiplying the vector. And it's also true the other way. And every function, you can define it using a matrix. And if you define a function in this way, it's actually going to be linear. So that's why matrices are what you call linear algebra. Maybe as like just as a side note, the power of what linear functions can do. So linear functions can rotate vectors, they can stretch vectors, they can reflect about certain axes going through the origin and many other things, but they can't really translate. So that's why when I gave the example before where I said if you add 5 here, then it's no longer going to be linear because I'm adding this sort of translation factor, which doesn't really make sense when you're talking about linear functions. Okay, so we've defined how to multiply a matrix with a vector, and now we're going to define how a matrix multiplies with another matrix, assuming that their sizes match up the right way. And it's just going to be a generalization of this, where you're going to be like multiplying A with the first column as a column vector, and then the second row is going to be a column vector. So let's take a look at what that looks like. So we'll do some motivation. If we have a matrix M, maybe you want to recursively apply M because it's some sort of process where you're tracking populations or something. And so you'd want to know what M squared is. Maybe you want to know what M to the power of N is going to look like. And so it's useful to know what matrix multiplication is going to give you, because you apply the function once, you apply it N times, and you want to know what it's going to be. Okay. So let's look at an example and motivate what we want this matrix multiplication to work out as. So we've got our matrix 4, -1, 2, and 1, and we're going to apply it twice to the vector x, which is xy. I prefer to write it as p because that's what it was in the original start of the course, start of this lecture. So when you multiply this matrix here with xy, we found that it gives you this one here. And then if we multiply it again, this matrix again with this vector that we've got here, because we've defined what matrix multiplication is with a vector, then we'll get this solution here. So that's 4 times this number plus -1 times this number. That goes in this position. and 2 times this number plus 1 times this number in this position here. And so this is going to give us this, which we can rewrite in this form here. And so what I'm trying to say is maybe we should define that m squared is going to equal this matrix here. So that's how we're going to kind of define our matrix multiplication. Okay, so matrix multiplying together gets a little bit complicated, especially when you write it in this sort of abstract setting, but when you work through examples, it's actually not too difficult to do. So if we have two matrices, we're only going to do it with square matrices, A and B. We're going to define the product, AB equals to some new matrix of the same dimension, and it's going to be given by Cij. It's given by the matrix Cij, and each entry Cij is given by the sum of these products. And you'll notice this is similar to the previous definition of products of matrices with vectors, but instead of having only one sort of column, we've got n columns, and so that's why we've added in another index, this sort of j that we need to work with. Okay, so let's have a look at how we do this multiplication. So this multiplication here, how we've defined it, all it's saying is this first entry, so the entry 1, 1 in our new matrix is going to be the sum of 4 times 4 plus minus 1 times 2. So that's that entry here. Okay, then if you want to do the second, the first row, second column, then you have to go kind of this row dot producted with this one here. So this is 4 times minus 1 plus minus 1 times 1. Okay, and then when you move to a new row and we want to sort of multiply this component with this component here, then we go 2 times 4 plus 1 times 2. So this is all this definition here says. I'm not sure it's that useful to memorize that. It's more useful to memorize sort of the process of how you do the matrix multiplication. So, so for the second row, first column entry, you take the second row and multiply it in some sense with this first column in the second matrix. So we get 2 times 4 plus 1 times 2. And then for the last entry, we've got 2 times minus 1 plus 1 times 1. Okay, and so maybe we can work through another example. If it's the first time that you've seen it, it's probably quite a lot to take in. So if we want to take the product of this matrix with this matrix, so these are different matrices this time, then we want to know what the entry here is going to be. Then it's going to be 1 times A plus 2 times C. And then we want to know what the first row, second column is going to be. So then we take the product of this with this. So that's 1 times B plus 2 times D. And then for the second row, first column, we've got 3 times A plus 4 times C. And for the last position, this second row, second column, we've got 3 times B plus 4 times D. Okay, so I think that's going to be it for the definition of matrix multiplication and basic examples of how you do it. So once we've defined the multiplication, then there's maybe this idea of if we have an identity matrix or not. So something similar to how 1 functions in the real numbers. If you multiply 1 with a number, then it's just itself. So we're going to, if you have a 2 by 2 matrices and you multiply them together, and if you look at this matrix here, which is just 1, 0, 0, 1, so it's 1s on the diagonal and 0s everywhere else, then you'll notice when you do the multiplication that you get 1 times A plus 0 times C, so this is an A, 1 times B plus 0 times D, so this is a B, 0 times A plus 1 times C gives you the C, and 0 times B plus 1 times D gives you the D. So it gives you back exactly the same matrix. And if you multiply from the other side, it actually does the same thing as well. So we're going to call this matrix the identity matrix, at least for the 2 by 2s. And so if we've got an n by n matrix, then we're going to define the identity matrix In. Maybe this definition's a little bit complicated, but the way that I would want you to think about it is you have your matrix on the diagonal entries. So when I is equal to j, we're going to put 1s. And then everywhere else, we're just going to put 0s. So I'll write a big 0 for every other position. So on the diagonal entries, so when I is equal to j, so the same number for the row and column, then you put 1s. And then otherwise, you're going to have 0s in those positions. That's the identity matrix of size n. So this is an n by n matrix. So we have examples here. So the identity matrix with shape 1 times 1 is just 1. The identity matrix for 2 by 2 matrices is this one here. For 3 by 3, it's this one here. And so, yeah, by applying our formula, we can immediately establish that for any n in n, the identity matrix exists, and it does have this property that when you multiply it with another matrix, no matter what that matrix is, as long as it's the right shape, then, and you can multiply it from either side, then it's going to give you back that matrix M again. And yeah, so sometimes if the context is clear, so we clearly know what size matrices we're working with, then we're going to sometimes remove this n and just write I. And sometimes you'll see that people write the identity matrix with this sort of bold face for the identity. Cool. Okay, so we've defined matrix multiplication, and well, it's much more complicated than if you're just multiplying numbers together. So one result that you need to know is the order of matrix multiplication does matter, so it's not commutative. So in general, m times n as matrices is not equal to n times n. So for example, if we take these two examples, if you multiply m by n, then you get 1, 2, 1, 2. Whereas if you multiply n times m, then you get 1, 1, 2, 2. And they're different matrices. On the bright side, it is associative. So the order that you do the matrix multiplication does not matter. So if you have 3 different matrices, m, n, and p, then m multiplied with the matrix n times p is equal to the matrix m times n times p. So this is called associativity. And yeah, one way you can prove this is because there's a one-way correspondence between matrices and linear functions. So there's a bijection between matrices of this size and linear functions acting on spaces of this size. And matrix multiplication reflects the function composition. So applying a function, then applying a function, then applying a function. And we know that function composition is associative. We've seen that before when we studied functions. Okay, another property that's a little bit weird compared to the real numbers is that we have 0 divisors. And what this means is if we have two matrices and they multiply to give us the zero matrix, so in a 2 by 2 matrix, I just mean something that looks like this. This doesn't mean that one of the matrices is the zero matrix itself. So it doesn't necessarily have to be this 0, 0, 0 for n or this 0, 0, 0 for n. It could be that they're non-zero matrices. And so we've got an example here. If you take m to be this 1, 1, 1, 1, and n to be 1, 1, minus 1, minus 1, multiply them together, you'll see 1, minus 1, so you get a 0, and so on, and you get zeros in every position. So you have to be careful. You can't make the same sort of deductions that you could do when you're working with just normal numbers. Okay, so we're going to do some motivation of inverse matrices. So this is going to be like the idea of the opposite operation of multiplying matrices, but it's a little bit more complicated. So let's have a look at some motivation. If you have a chemical reaction and you've got two reactants, R1 and R2, and you have this sort of restrictions that you want the quantity of R1 should be twice the quantity of R2, and then the quantity of product is then equal to half the quantity of R1 plus 1/3 of the quantity of R2. So they react together, they give you some product, and how much do you get? It's half the quantity of R1 plus 1/3 of the quantity of R2. And then the question is, what quantities of R1 and R2 should be used to make sure that we produce 5 units of our product that we want? And so we'll write out this in equations. So from A, this one here, we know that R1 is twice the quantity of R2. So this is x equals to 2y. From B, we have that half of R1 plus 1/3 of R2 is equal to 5 because we want to produce 5 units. So that's sort of our I guess, simultaneous equation setup. And all that I've done here is I've multiplied this equation here by 6, and I've taken 2 from both sides on this equation here, just to make the arithmetic look nicer in this matrix. So you can solve these equations by eliminations. So substitute maybe x equals 2y into this equation. But when you're working with computers and stuff, working with matrices and doing row reductions and stuff is easier. I'm sure most of you have seen that before, but if not, don't worry about it. We don't need to cover that in this course. So instead, we could try and solve this problem here, because this equation, these equations here, is exactly the definition of this, because we would have 1 times x minus 2y equal to 0, and then 3x plus 2y equal to 30. And, well, can we solve this equation by just using matrices? And so if you had an equation that looks like maybe real numbers, so n times x is equal to m, then of course you would just divide through, assuming that n is not equal to 0, you would divide through by n, and so you'd get x is equal to m on n. And so what we want to do is we want to be able to divide this sort of thing over to the other side. And the way that we do that is with inverse matrices. And so this is kind of what I've just described there. And the answer, again, is, well, we can sometimes do it just like in real numbers. You can't divide by zeros or something like that. But usually when you have 0 times something, then you don't need to worry about that equation. But in this, maybe it's more common because you have a matrix A times x equal to some column vector B. And, well, maybe A, you can't actually divide it over in some sense. It doesn't have an inverse, even though it might not be the zero matrix. And so the process that we do is we find this inverse matrix, which we'll call A inverse. And so we start with this equation here. And then we'll multiply both sides by its inverse. And then what happens is this actually reduces down to the identity matrix. And then the identity matrix times a column vector is equal to the vector itself. Okay. So from our previous example, we had this matrix here, 1, -2, 3, and 2. And what we're going to find out is we can actually invert it. So we take the power of -1, and we get this matrix here. And we're going to have a formula for this later on, which you'll see. It's not too complicated. All that's going on is you switch like these two, you take the negatives of these two, and then you have this sort of equation of 1 over something called a determinant. But suppose that we're being given this fact. If we want to solve our equation that we had before, we can just take this matrix and multiply it by b, and we've solved what our x and y need to be in our vector. And so, yeah, something that I've hinted at before is if you have a matrix A, we're going to define its inverse, if it exists, as the matrix of the same size. So it's going to be an n by n matrix as well. And it's going to have this property that if you multiply it, the inverse with the original matrix in any order, then it's going to give you the identity matrix. And so this is just another way of writing what I wrote up before here. If an A inverse exists and we have AX equals B, and we want to solve for our vector x, then what we can do is we can go x is equal to the identity times x, which is A inverse times A, which is equal to A inverse times AX, and then we substitute out the AX for B using this equation here. And so we find out that x is equal to A inverse B. Cool. Okay, does anyone have any questions about these inverses other than, well, I'm going to have to teach you how to find them? Okay, so this restriction of whether a matrix has an inverse or not, and you're only going to be doing inverses of square matrices, is based on whether a particular number from the matrix is 0 or not. So if we have the 0 matrix, and say, maybe for example, if we have the matrix 0 of 1 dimension, clearly this is not going to be invertible because the matrix multiplication is going to be the same as multiplying real numbers. And so, yeah. So this is not going to be invertible because 0 is not invertible. And in a similar way, you can't find an inverse for the 0 matrix. So if you had something like 0, 0, 0, 0, this multiplied with any other matrix A, or even a vector xy, this is always going to be 0, 0, and this is always going to be 0, 0, 0, 0. So 0 matrices are always 0, so there's not going to be an inverse because you can never get the identity out. So how are we going to determine if A has an inverse? And the answer is this function called the determinant of a matrix. And if it's 0, then it's non-invertible. If it isn't 0, then it is invertible. Okay. So there is a formula for if you have an n by n matrix. We're not going to cover that in the course. It's a little bit complicated. But in this course, we're going to focus on 2 by 2 matrices. And so the determinant of a matrix A is going to be given by number in Q, which is A times D minus B times C. A times D minus B times C. So, as an example, what's the determinant of this matrix here? 1 times 2 minus 2 times 3. So that's 2 plus 6, which is 8. So this matrix here is invertible. And we have this kind of cute result that if you have two matrices, this even works if you have n by n matrices. But for this course, we're only worried about the 2 by 2s. The determinant of A times B is equal to the determinant of A times the determinant of B. And, well, for this, I recommend going through the proof. You can prove this, so just take some general matrices A and B and apply this formula here and prove that these are equal. Okay. So I haven't proven that the determinant does decide whether or not it is 0, or determines whether it's invertible or not, depending if the determinant 0 or not, but I'm just telling you that it is. This course is, hey, yeah. Yeah. It just means 2 by 2 matrices. Yeah. Yeah, so n by n, it's true. Yeah, yeah. It's very, very common to use that fact in linear algebra. So, yeah, no matter what the size of the matrix is, you're going to have this result, as long as the A and the B are of the same size. Yeah. Yeah, so the determinant is usually defined on a square matrix, and inverses are usually defined on a square matrix. Of course, there's always, like, you can do special tricks and make up a new definition that's slightly more general, and they probably exist, but it's not something that's commonly taught, and it only appears in special cases. Okay, so if we know that a matrix has an inverse or not, then one question is the matrix, the inverse unique? So if we pretend we have two different matrices that are the inverses of A, so we've got B and C, and we're going to pretend that B times A is the identity and A times C is the identity, then we're going to actually find that B is equal to C, and so we're going to have uniqueness of inverses. So if you look at B, B is equal to B times the identity, which is equal to B times AC, because AC is equal to the identity. Then we're going to use the associativity of matrix multiplication. So we're going to change the order of our multiplication. And then, well, BA is equal to I, and so we've got I times C, which is equal to C. And so this proves that inverses are unique. So, yeah, if you've got a matrix A, if you want its inverse, then it is actually it's not just a inverse, there is a unique one. And I'm just going to give you the sort of formula for how do you calculate the inverse. And if we have a matrix A, and we're only going to focus on 2 by 2 matrices, it has an inverse if and only if the determinant is non-zero. And in this case, the inverse is given by this formula here. So you switch the A and the D, and you take the negatives of the B and the C, and you divide through by the determinant. So you'll notice that this formula actually fails to make sense if the determinant's 0, because you've got 1 over 0. So you're never going to have an issue of you trying to invert a matrix that you can't. You're not going to get an answer out of this formula because you're always going to end up with 1 over 0. So we've got an example here. If we've got the matrix 1, minus 2, 3, and 2, then This is, if you invert that matrix, then you calculate the determinant, which is going to be 2 times 1. I'll just finish up now. 2 times 1 minus 2 times 3, which is equal to 2 plus 6. So that's that 8 here. And then we just switch the 1 and the 2, and we take the negatives of the minus 2 and the 3 to get those ones there. Okay, so I'll finish here. We'll finish this off tomorrow. Thank you.